Now, in the previous lecture we have derived numerical integration formulas for evaluating an improper integral, and the improper integral that we have considered was of the form 0 to infinity f x dx, and for evaluating this integral we have written a formula of the type lambda 0 f x 0 plus lambda 1 f x 1 plus so on plus lambda n f x n. The formulas that we derived we call them as the Gauss-Lagrange quadrature rules, and these formulas depend on the Lagrange orthogonal polynomials. We have derived the 1 point 2 point formulas, and we have used the weight function here as exponential of minus x. If the weight function is not available, we said we shall supply the weight function so that we can use this formula, so that we write it as exponential of minus x into exponential of x f x dx, and then we consider this as a new function as 0 to infinity exponential of minus x g x dx. Then we can apply the formula that we have derived here on this new function. Now, let us illustrate it by taking an example on this. So, let us take this example. Evaluate, let us take a simple example, exponential of minus x upon 1 plus x squared dx. Let us take 1 plus x squared by, let us give the formula also, Gauss-Lagrange 2 point formula. Now, here we have been provided in the suitable form, therefore, we simply have f x is equal to 1 upon 1 plus x squared. Therefore, I can evaluate the integral by using the 2 point formula. The 2 point formula we had written was 1 upon 4 2 plus root 2 f of 2 minus root 2 plus 2 minus root 2 into f of 2 plus root 2. Now, we would like to substitute this in the function and then simply evaluate them. So, what we would therefore have this is equal to 1 upon 4 2 plus root 2 and 1 upon 1 plus 2 minus root 2 whole square plus 2 minus root 2 into 1 upon 1 plus 2 plus root 2 whole square. We just simplify this, and that is the required solution 1 upon 4. This is actually comes out to be 2.54145 plus 0.0628, and this is 0.64706. This result may not be of the required accuracy. The computation can be done using the 3 point or the 4 point formulas. The computation can be stopped when the magnitude of the difference of two successive values of the integral is less than the given tolerance. Now, let us take an example in which the weight function is not given to us, is not provided in the suitable form. Evaluate 0 to infinity 1 upon x squared plus 1 dx using the 2 point Gauss-Lagrange formula. Now, here I have not been provided the weight function. So, therefore, we would write this given integral as dx upon 1 plus x squared as equal to 0 to infinity exponential of minus x into exponential x upon 1 plus x squared dx. Now we choose this as our function f x. Therefore, f x is e to the power of x upon 1 plus x squared. Now we shall use f x as exponential s divided by 1 plus x square in the 2-point rule that we have derived earlier. So, the value of the integral I is 1 upon 4 2 plus root 2 into exponential of 2 minus root 2 by 1 plus 2 minus root 2 whole squared, 2 minus root 2 exponential of 2 plus root 2 by 1 plus 2 plus root 2 whole squared. This can be evaluated and I will give the result, you can compute it. This comes out to be 1.49326. Now, in this case you can actually compare your solution with the exact solution, we have taken it in way. This is simply tan inverse of x 1 upon 1 plus x squared. So, I will have this exact result as tan inverse of x from 0 to infinity, tan inverse of infinity is pi by 2 and tan inverse of 0 is equal to 0. So, it is pi by 2 is the exact solution of this problem. This is approximately 1.5 something. So, we can compare the two results. Notice that the abscissas 2 plus root 2 and 2 minus root 2 are not covering the domain 0 to infinity sufficiently. Here it is like approximating infinity as 2 plus root 2. To obtain more accurate results, we should choose formulas with more abscissas. Then the abscissas cover a larger domain. The largest value of the abscissa can be sufficiently big for a higher order formula. For example, if we have n is equal to 5, that is a 6-point formula, the largest abscissa is 15.98. The largest weight corresponds to the smallest abscissa. The values of the weights decrease with respect to the larger abscissas. The smallest weight is obtained corresponding to the largest abscissa. Now, let us take the next improper integral, that is evaluating minus infinity infinity of a particular form, and we would consider the formulas of this particular type w x f x dx, and we shall choose w x as exponential of minus x squared, exponential of minus x squared f x dx. And this we would like to write again as lambda naught f x naught plus lambda 1 f x 1 plus so on lambda n f x n. This group of formulas are called the Gauss-Hermite quadrature rules. These are called the Gauss-Hermite quadrature rules. Gauss-Hermite quadrature rules. That means the weight function in this case is exponential of minus x squared. The weight function is exponential of minus x squared. The orthogonal polynomials here are the Hermite polynomials. Orthogonal polynomials or the Hermite polynomials which are denoted by h n plus 1 x. The orthogonal property of this Hermite polynomials is integral of minus infinity to infinity exponential of minus x squared h m x h n x dx is equal to 0 for m not equal to n. So, this is the orthogonal property of the Hermite polynomials. Now, let us define what is the Hermite polynomial. Let us just take few of the Hermite polynomials. The Hermite polynomial is defined as this. So, h n plus 1 x is given by minus 1 to the power of n plus 1 exponential of x square outside d n plus 1 upon dx n plus 1 of exponential of minus x squared with h naught is equal to 1. This is again similar to the Rodriguez formula for the Legendre polynomials, which is also similar for the Laguerre polynomials. So, all the Hermite polynomials can be generated just using this particular formula. Let us take few of this and then construct our quadrature rules. So, let us write down what is our h1x. I have to take n is equal to 0 over here. So, I will have minus sign here, exponential of x squared d upon dx exponential of minus x squared. So, I have this as exponential of x squared. I differentiate this exponential of minus x squared minus 2x. So, h1x is simply 2x. Now, let us take one more polynomial. h2x is n is equal to 1, therefore, I have a plus sign here, then you have exponential of x squared d square upon dx squared exponential of minus x squared. So, let us evaluate this exponential of x square d upon dx exponential of minus x squared into minus 2x. Let us take this minus 2 outside and then I have exponential of x squared, then I have differentiate this as a product. So, exponential of minus x squared into 1 plus x into e to the power of minus x squared minus 2x. I have taken it as a product of x into exponential of minus x square, exponential of minus x square into 1 plus x into this product. Now, exponential of x square again cancels and let us retain this 2 outside, take the minus sign inside, 2x minus 1, 2x squared minus 1, or we can write it as 4x squared minus 2. Now, this 2 is outside, so let us retain 2 as the quantity that is outside. Now, I can similarly show, let me just give what is this h3x, it is 4 into 2x cubed minus 3x. Now, when once we write down these Hermite polynomials, let us now write down what are the abscissas in our quadrature rule. The abscissas are zeros of h n plus 1 x, zeros of h n plus 1 x is equal to 0, and the weights as we have done last time we use the Lagrange fundamental polynomial form. So, lambda k will be minus infinity to infinity the weight function exponential of minus x squared h n plus 1 x divided by x minus x k into derivative of h n plus 1 x k dx. So, these will be the weights for the Gauss-Hermite quadrature rule. We have been using all through, whether it is Legendre, Chebyshev polynomials or the Laguerre formulas, we have been using this as p n plus 1 and this is p n plus 1 prime of x k. Now, let us obtain few rules. So, let us use this and write down the 1 point rule, 2 point rule and 3 point rule. So, let us take 1 point rule, that means n is equal to 0, h1x is equal to 2x we have taken. Therefore, let us substitute lambda 0 is minus infinity to infinity exponential of minus x squared 2x by x minus x 0, therefore, this is x. The zeros of this are, if you put it as equal to 0, we simply get x naught is equal to 0 as the abscissa of this. Now, this is x minus x 0, that is x, and derivative of this is simply 2. So, 2x cancels, I simply have this as minus infinity to infinity exponential of minus x squared dx. This we know that this is equal to root of pi. Therefore, our integration rule is exponential of minus x squared fx dx is the weight is root pi, f of abscissa is 0, f of 0 and the order of the formula is 1, order of the formula is 1. Now, you can see it looks like a midpoint formula, 0 is the midpoint, minus infinity to infinity. So, it is almost like a midpoint formula that we have. So, let us take a 2-point rule. So, we have here n is equal to 1, therefore, h1x, h2x is equal to h2x we have derived as 2 times 2x squared minus 1. Therefore, the abscissas, let us write down the abscissas by putting h2x is equal to 0, we get from here x is equal to plus minus 1 upon root 2. Therefore, I can take x naught is equal to minus 1 upon root 2 and x 1 is 1 upon root 2. Then as we have done in the previous cases, let us write down this leading coefficient as 1. So, let us take 4 outside, so that I can write this as x minus x naught, x minus x 1. Now, let us write down our weights. The let us also we also need our derivative. Let us write down the derivative also. h2 prime of x is equal to, let us take from here, this is equal to 8 times x, this is simply 8 times x. So, let us write down lambda naught, that is minus infinity to infinity exponential of minus x squared into h2x is x minus x naught, x minus x 1 divided by x minus x naught, and derivative is 8x, therefore 8x naught. Now, x minus x naught cancels with x minus x naught. Let us take this constant outside. So, I will have 1 upon 2 times x naught coming from here. This is minus infinity to infinity exponential of minus x squared. Let us open it into 2 integrals, into x minus exponential of minus x squared into x 1 dx. I just multiplied exponential of minus x square into x minus exponential of minus x square into x 1. Now, this is an odd function in minus infinity to infinity, therefore, the value of this integral corresponding to this is equal to 0. So, only this will contribute, and let us take minus x 1 outside. So, I will have minus x 1 upon 2 x naught minus infinity to infinity exponential of minus x square dx. Now, this is equal to now let us take the ratio of x 1 and x naught, these are in magnitude same, its ratio is minus 1. So, the ratio is minus 1, so it will have plus half and this is root of pi. Therefore, we have lambda 0 is equal to root pi by 2. Now, lambda 1 we can just look at this one, we have the numerator is same, denominator is x minus x 1 and this is 8 x 1. Therefore, x minus x 1 cancels and I will have here x 1 here. So, let us write down this particular step. Therefore, this is 2 times x 1 minus infinity to infinity exponential of minus x square into x exponential of minus x square x naught dx. So, x minus x 1 cancels with this, the numerator will be left out with x minus x naught. So, that is x minus x naught, denominator is equal to x 1. Again for the same reason, this is an odd function, therefore, the value of this first integral is again 0. I take out minus x naught out, so I will have x naught upon 2 x 1 minus infinity to infinity exponential of minus x squared dx, and the ratio is minus 1, therefore, again I get this as root pi by 2. Therefore, our formula is integral minus infinity to infinity exponential of minus x squared f x dx. Both the weights are same, root pi by 2, f of minus 1 upon root 2 plus f of 1 upon root 2, and the order of this formula is 3. Now, you can see that these are evenly distributed, symmetrically placed about the origin. This is minus 1 upon root 2 and 1 upon root 2 are the two abscissas. Now, as you go to the 5-point formula or the odd ones, if you take 9-point formula, all of them would be symmetrically placed, one less than 0, one greater than 0, they are symmetrically placed about the origin. And as we take the order of the formula higher and higher, the value of this abscissa would grow larger and larger to cover more domain, so that the result will be much more accurate. Let us take a simple example on this. Now, in this case again, if the weight function is not available, we shall provide the weight function for it. So, let us take evaluate minus infinity to infinity exponential of minus x squared upon 1 plus x squared dx using 2-point Gauss-Hermite formula. Now, here it is given in the suitable form. So, we can straight away pick up what is our f x, that is 1 upon 1 plus x squared. Therefore, our given integral I is equal to, we shall use this particular formula that we have just written, that is 2-point formula root pi by 2 f of minus 1 upon root 2 whole squared, that is simply 1 upon 2 plus 1 upon 1 plus 1 upon 2. I have taken 1 upon root 2 whole square, written it as 1 upon 2 of this. So, this comes out to be simply 1.18164. Now, so far we have derived the number of formulas, and then we said that these formulas have got precision 2n plus 1 or order 2n plus 1, which implies that these formulas would integrate exactly polynomials of degree less than or equal to 2n plus 1. That means, if I set up the f x is equal to 1 x square x to the power of 2n plus 1, I will get the left hand side is equal to right hand side identity, therefore, it integrates exactly. Now, how do we get the error terms for these equations? The error term is again from the first principles, we shall do it, and let us just illustrate as an example how do we get the error term in all these quadrature rules that we have derived. Now, as I said, these are formulas of order 2n plus 1. Therefore, they integrate exactly polynomials of degree less than or equal to 2n plus 1. That means, if I take f x is equal to 1 x squared so on x to the power of 2n plus 1, then these formulas will integrate exactly. Now, if I want the error term, therefore, I should take the next power of x, that means to get the error term I would take f x is equal to x to the power of 2n plus 2 and find out the error constant. Therefore, we substitute this and find the error constant, and error constant is c. And what is this c? This c is equal to whatever the formula that we have here, integral a to b w x f x dx. Now, this is one of these formulas that we have now derived, this one, and bring the right hand side to this. So, this is lambda naught f x naught lambda n f x n. Now, I am substituting f x is equal to x to the power of 2 n plus 2 here. So, I am replacing f x by x to the power of 2 n plus 2, and I am replacing all these by x to the power of 2 n plus 2. This is our error constant. Then the error is given by r 2 n plus 2, it will be 2 n plus 2. This is equal to c upon 2 n plus 2 factorial and 2 n plus 2 derivative of xi. Xi is lying between the a and b. This is the general procedure for every method, that we pick up this order of the formula and then find out the error constant and write down our final error formula here. So, let us illustrate it through an example. So, let us take this as an example. Find the error term in the, let us take a Gauss legend Lagarre, let us take Gauss Lagarre 2-point rule, that is 0 to infinity exponential of minus x f x dx is 1 upon 4 2 plus root 2 f of 2 minus root 2 2 minus root 2 f of 2 plus root 2. It is given that it is of order 3. It is given that the formula is of order 3. Now, since the formula is given to us as order 3, it is going to integrate exactly f x is equal to 1 x x square x cubed. Therefore, the error term should come from the next power, that is f x is equal to x to the power of 4. Therefore, let us write down, since the formula integrates polynomials of degree less than or equal to 3 exactly, that is n is equal to 3. Let us take exactly set f x is equal to x to the power of 4. So, we will take f x is equal to x to the power of 4. Therefore, our error constant should be 0 to infinity exponential of minus x x to the power of 4 minus, we bring everything to the left hand side, 1 upon 4 2 plus root 2, and f of x should be x to the power of 4, that is 2 minus root 2 to the power of 4 plus 2 minus root 2 into 2 plus root 2 to the power of 4. Now, you can integrate this. Let us, I will give you the value of this. If you just integrate it, this is what you get, minus of x to the power of 4 or 4 x cubed, then you have 12 x squared, then you will have 24 x, then you will have 24 e to the power of minus x. That is because you are integrating by parts. So, this will be the first integral is minus x to the power of 4, then it is 4 times 4 into x cube, this is 12 x squared, 24 x, 24 this one, and this is evaluated between 0 to infinity. And the second term is 1 upon 4. Let us take 2 at a time. This, let us take 2 plus root 2 into 2 minus root 2. combine them, that will be 4 minus 2, that is 2. So, what is left out is whole cubed, and again I combine these two to give a 2 and 2 plus root 2 whole cubed. I am combining one factor each, so that they get simplified. Now, at infinity this is entirely, this is 0, at 0 all of them 0 except 24. So, what is left out is simply 24 into 1, that is simply 24, that is what we get from the first bracket here, and the second bracket is 1 upon 4. Now, these are, this is odd power 3. So, all these odd ones will cancel off, that root 2 1 will cancel, and what I get here is I will give the value of this, this gives you 40 minus 28 root 2, and this will give me 40 plus 28 root 2. This is the expansion of this, the expansion of this. Therefore, 28 root 2 cancels off, we will have 80 by 4, that is 20, divided 24 minus 20, that is simply equal to 4. Therefore, I have the error term given as R4 is C by factorial 4 F4 of xi, that is 4 cancels. So, I will have 1 upon 6 F4 of xi, xi lying between 0 and infinity. Therefore, this is how the error can be obtained for any particular formula. So, the main thing is, when once you have to, you find the order of the formula correctly, then I can immediately use the next power of x as the required function f x, find the error constant, and then write finally the error of this formula. If the integral that is given to you does not fit into any one of these forms that we have considered, then we have to construct some special formulas. For example, we have integral a to b w x f x dx, where the weight function w x is not one of the forms that we have considered. The integration rule should contain only f x, not the weight function. Then one has to construct one's own formula. It is always done in many of the practical applications by just applying the fundamental principle. The fundamental principle is, if there are 2n plus 2 parameters, we just have to make it exact with f x is equal to 1 x square x to the power of 2n plus 1 to get the required number of equations for required number of parameters, solve them, and that will be our formula. Therefore, it is possible for us to construct our own formula for any given w x irrespective of whether orthogonal polynomial exists or not. In that case, orthogonal polynomials may not exist at all. So, we will call this as method of undetermined coefficients, method of undetermined coefficients. Now, let me first, I will take two examples. Let me first take an example which we know already, the formula which we know already. So, derive the quadrature rule. Let us take the one that we know very well, minus 1 to 1 f x dx is lambda 0 f x 0 lambda 1 f x 1, such that it is of highest possible order Find the error term. In all these cases, the error term is very important, because that will really tell you the not only order it gives you, and what is the error constant, that is the constant that is multiplying the error term. Now we first look at the formula, how many unknowns are there. We have got lambda 0 to be found, lambda 1 to be found, x 0 to be found, x 1 to be found. Therefore, there are 4 parameters. Therefore, we need 4 equations. Now since we need 4 equations, I must make it exact with f(x) is equal to 1 x x square x cubed. So each one will give us an equation. So I will get 4 equations in 4 unknowns. If any one of them turns out to be 0 is equal to 0, so we do not have an equation, so I will go to the next one, x to the power 4. Now let us do this. So let us put f(x) is equal to 1. Then the left hand side is minus 1 to 1 dx. Now left hand side is minus 1 to 1 dx, that is equal to 2. We evaluate it, integral is equal to 2. f(x) is taken as 1, so this is lambda 0 plus lambda 1. Let us take f(x) is equal to x. This gives us minus 1 to 1 x dx, odd function minus 1 to 1 0, and this is equal to lambda. Now f(x) is equal to x, therefore this gives you x naught, this gives you x 1. So lambda naught x naught, lambda 1 x 1. Now let us take f(x) is equal to x squared. So I will have minus 1 to 1 x squared dx. Now this is x cubed by 3, so I will have here 2 by 3, lambda naught x naught square plus lambda 1 x 1 square. Then I take f(x) is equal to x cubed, therefore minus 1 to 1 x cubed dx. This is again an odd function in minus 1 to 1, so I will have a 0 here, and this is lambda 0 x 0 cubed plus lambda 1 x 1 cubed. Now these equations, at the face of it they look very difficult to solve because they are nonlinear equations, but because of the way that the right hand sides are there and the coefficients here, the solution of this can be done very easily in a very systematic way. Now first let us consider these where you have got zeros, that means equation 2 and 4. Let us eliminate x naught from here. So what I would do is I will take the equation 4 and then multiply by x naught square to eliminate the first coefficient. So I will multiply 2 into x naught square, 4 minus 2 into x naught square, and that gives me lambda naught x naught cubed, lambda naught x naught cubed cancels. So what I will have here is lambda 1 x 1 cubed minus lambda 1 x 1 x naught square is equal to 0. The right hand sides are 0, both are 0. So this will be simply lambda 1 x 1 cubed minus lambda 1 x 1 into x naught square. Let us simplify this. This is lambda 1 x 1 square minus x naught square. So let us write down one more step and put it equal to 0, x 1 minus x naught x 1 plus x naught is equal to 0. Now in the method that is given us to us, this is the method that we have been asked to derive. Lambda naught lambda 1 they are not equal to 0, these are distinct abscissa, so x naught is equal to not equal to x 1. Therefore we need to consider that here, that x naught is not equal to x 1, that is given in the problem. The weights are not equal to 0, so lambda 0 is not equal to 0, lambda 1 is not equal to 0. So these are all the properties of the given quadrature rule. If that is so, you can see that x 1 is not equal to x naught, so this factor can be cancelled. Lambda 1 is not equal to 0, so it can also be cancelled. So what is left out is simply x 1 into x 1 plus x naught is 0. Now we shall exclude, this gives you x 1 is equal to 0 or that is 0. So x 1 is equal to 0 or x 1 is equal to minus x naught. Now we shall exclude x 1 is 0 because just look at 2 here, when x 1 is equal to 0 this goes off, and hence lambda naught is equal to 0, that is not possible, lambda is not equal to 0, or x0 is equal to 0. If x0 is 0, again x0 is 0, x0 x1 is equal to 0, both are equal. Therefore, this is also not possible. Therefore, the only is x1 must be equal to minus x0, that is the only solution that comes from here. Let us substitute in 2, x1 is equal to minus x0. Therefore, that gives you lambda naught minus lambda 1 is equal to 0, or lambda naught is equal to lambda 1. I have substituted in 2. So, x1 is equal to minus x0, x0 is common, cancel off x0. So, we have lambda naught is lambda 1. When once we get this value, I can substitute in 1, lambda naught is equal to lambda 1. So, I will get from 1 they are equal and 1. Therefore, from 1 it gives you lambda 0 is equal to 1, lambda 1 is equal to 1. Now, we can use equation 3. Since lambda 0 is equal to lambda 1 is equal to 1 and x0 is a minus x1, I have simply twice x0 square is 2 by 3. So, I am just substituting in this. So, this gives you x0 square is 1 by 3, x0 is plus minus 1 upon root 3, and x1 is equal to minus x0. So, I will have the opposite sign. So, I choose x0 as one of them, either plus 1 by 3 or minus 1 by 3. So, if I take x0 is minus 1 by 3, I would get this as 1 by 3, or conversely I will get the reverse one, but the formula will be same because lambda naught is equal to lambda 1. Therefore, we have derived the formula minus 1 to 1 f x dx, lambda naught is equal to lambda 1, that is equal to 1. So, simply f of minus 1 by 3 plus f of 1 by 3, which is nothing but the our Gauss-Legendre 2-point rule, which we have already proved this point. Now, let us take the error term. So, I have to take f x is equal to the next power, that is x to the power of 4, and therefore, the error constant c would be minus 1 to 1 x to the power of 4 dx minus when x to the power of 4 it is even. So, both will be equal, 1 upon root 3 to the power of 4. This is x to the power of 5 by 5, therefore, 2 by 5 minus 2 by this gives you 9, this gives you 9, that is equal to 18 minus 10, that is 8 upon 45. Therefore, we have the error term R4 is c by factorial 4, fourth derivative at a point xi, that is 8 upon 45 into 24 f4 of xi, or 1 upon 135 f4 of xi, xi lying between 1 and minus 1. So, this is how we can get the error constant, and using the error constant I can now get the error term for the given formula as this, and then write down this one. So, that completes the error term also, and you will see that the multiplicative factor of f4 is 1 upon 135, which is quite small. So, that is how we can see how the error would now decay as we go along, and we can use here also, as we have done in the earlier also we have shown, we can break this up into a given interval a to b, we can break it into some a to c, c to b, and then use a composite rule also, so that the error would be much smaller. Now, let us give one last example. In
last example, the order was
3. The order is 3. Therefore, the error term should get from f x is equal to x to the power of 4. So, let us take one more example. So, we will say this is calculate the weights, abscissas and remainder term in the Gaussian quadrature formula 1 upon root pi 0 to infinity e to the power of minus t by root t f t is a 1 f x 1 a 2 f x 2. Now, this does not belong to any of the classes that we have described earlier, even though it is 0 to infinity, but this is not the e to the power of minus t form, therefore, it is not Gauss-Lagrange. Therefore, for this the only way is that we have to go through this undetermined coefficient procedure. Again we have 4 constants, therefore, we have 4 parameters here a 1, a 2, x 1, x 2. Therefore, we make it exact with f t is 1 t t squared t cubed t square t cubed. There are 4 parameters, so we get 4 equations. So, let us substitute them. So, f t is equal to 1, this is 1 upon root pi 0 to infinity e to the power of minus t. I will take this up and write it, that is t to the power of minus half into dt. I just take it off and this one, and this is equal to a 1 plus a 2 f of x 1 is equal to 1, this is also equal to 1. Now, we would like to use the gamma function definition of gamma function and evaluate this as a gamma function. If you remember the gamma function, gamma of alpha is 0 to infinity x to the power of alpha minus 1 exponential of minus x dx. But gamma alpha plus 1 is equal to alpha gamma alpha. We need here in particular what is the value of gamma half, that is equal to root of pi. So, I would like to use this particular property to evaluate this completely, that is gamma half is equal to root of pi, gamma of alpha plus 1 is alpha gamma alpha. Now, if you see this definition of this is x to the power of alpha minus 1, therefore, I need to have here gamma of we have minus half here. So, if I take alpha is equal to half here, then I will get minus half. So, alpha is equal to half, it gives me gamma half. Therefore, the left hand side is 1 upon root pi gamma of half, and the right hand side is a 1 plus a 2. And gamma half is root pi, therefore, root pi cancels. I have the first equation as a 1 plus a 2 is equal to 1, a 1 plus a 2 is equal to 1. Now, the remaining equations are easy for us to do it. F t is equal to t 1 upon root pi 0 to infinity exponential of minus t. Now, I have got here f t is equal to t, therefore, root t cancels, I will have t to the power of half in the numerator, t to the power of half dt, and the right hand side is a 1 x 1 plus a 2 x 2. Now, let us evaluate the left hand side here. This is 1 upon root of pi, this is gamma of 3 by 2, this is 3 by 2 minus 1, that is half. Therefore, this is gamma 3 by 2, that is 1 upon root pi, and we will use the property that gamma 3 by 2 is half gamma half, this gives you half gamma half, that is equal to half gamma half is equal to root pi. Therefore, this is equal to half. Therefore, the second equation is a 1 x 1 a 2 x 2 is equal to half. And I will similarly I will give the remaining equations. You will get a 1 x 1 squared a 2 x 2 squared is equal to 3 by 4, that is equation 3, a 1 x 1 cubed a 2 x 2 cubed is equal to 15 by 8. You will have to follow exactly the previous method that we have done here, that we take the first and third equation eliminate x 1, second and fourth eliminate x 1, then eliminate a2 x2, it will get a single equation in x1 or x2, and that will be give the solution of the problem, and the equation for your verification, the equation comes out to be same, and because of the symmetry you will get the same equation for x2 also. Both the equations will be the same. Obviously the because of the structure of the formula, the one will be one of the roots, the other will be x1. Therefore the two roots are x1 is 3, I am solving this and writing it 3 minus root 6 by 2, and x2 is equal to 3 plus root 6 by 2, and I can find out the then substitute back the values and then get my values of a1 a2. a1 is 3 plus root 6 by 6, a2 is 3 minus root 6 by 6. So let us just finally write down the formula, root pi 0 to infinity exponential of minus t by root t dt is 1 upon 6, because a1 a2 it has a minus 1 by 6, 3 plus root 6, that is this coefficient, and f of x1 that is 3 minus root 6 by 2, and the second one is plus 3 minus root 6, that is from a2, this is f of x2 that is 3 plus root 6 by 2, and of course order we made it as 3, order is 3, and find out the error constant by taking the next term, that is t to the power of 4, and what I would get here is simply c is 24 upon 16, 24. So that the remainder is 1 upon factorial 4 24 by 16 f4 of xi, that is simply 1 upon 16 f4 of xi. Therefore what we are trying to say here is that if any practical application, if the weight function is not of the suitable form, one can construct his own quadrature rule that fits that particular application problem, and then they follow the procedure, the fundamental definition of what is a quadrature rule, that it should integrate polynomials of degree less than or equal to some 2n plus 1, then you will be able to get any integration rule you want for any application. So we will now close with this. Thank you.